Hi there, my name is Xiaolei. Today I will use a relatively new tool called Apache Pulsar to solve a problem that troubles me every day. The problem is, should I wait in line for a restaurant or not? Yeah, I live in San Mateo, so I have to wait 2 hours to get sushi. But do you really want to go to the place next door where nobody's eating? Probably not. So what you really want to find is a place which is usually popular, but happen to be nobody there dining today. Now, the way I do it, I remember a number of people at every place, every day, and I look back at the history, and if I find a place that's usually pretty popular, and the line just half as long, I hop in. How do we do this with data then? Well, we can use the historic check-in data from Yelp to simulate this. We count the number of check-ins at each businesses for 1 hour period, and that gives us an estimation of how many people are there. Then we look at the same number in the past 3 months and take the maximum of that number to reveal the maximum capacity of the place. By doing a division, we see how full a place is. Now, let's first look at a very brief demo. Here on the upper panel, you see the current busy ratio of all the restaurants. This is in Las Vegas, updated every second. You can see that some of them are getting full, and the other ones are pretty empty. And down here, you can see the current throughput of the system, and you can find a few controls that we can even modulate how fast data are piping through the system. For example, we can increase the throughput, increase the ingestion rate into the system, and you can see that there are much more data coming in. At the same time, the latency will be going up. You have a back pressure, and you can solve that by having higher parallelism. Right. So you can control, monitor the system while you're using it. Now, back to the presentation. As I mentioned before, this is achieved by a relatively new tool called Apache Pulsar. Now, Yelp's data contains 200,000 businesses, but there are only 11 cities in the data set. So that is much smaller than the number of cities in the world. So we play this data set 10,000 times faster than its original timestamp at 5,000 events per second to simulate a global scale data set. Now, this is a really high throughput system, and Pulsar can handle this much like Apache Kafka, which is also a high-performance messaging framework. Now, these two tools are very similar. The main difference is that Pulsar, unlike Kafka, will only acknowledge a message when it is already persisted into a number of storage nodes. Now, Kafka actually acknowledges a message whenever it's already cached in memory. So if you turn off the power of a Kafka cluster, you actually lose some messages. This is not going to happen with Pulsar. However, with that stronger guarantee, you have a higher latency, but a 30 microsecond latency, as we measure here, is not really a problem for us. Especially, we really only care about second level response time. Now, there's also many other features. For example, Pulsar Functions allow you to register a calculation into Pulsar that is triggered by messages. That means you write a Python or Java function, save that into Pulsar storages, and that function will be loaded up whenever a message comes in a specific topic. Here we have a topic that processes the restaurant's profile information, that their name, location. It does geospatial indexing and save that to a Redis store. Now, more interestingly, we have the check-in events processed by another set of functions, which counts the number of events in 1 hour windows for all of those 200,000 businesses. Now, the result is published in another topic, which is then triggering another set of functions. We calculate the max of that count over a 3-month period. Now, this is a really long period, and you're looking at between 10 to 50,000 events that you have to count and find the maximum. So you cannot do this in a trivial manner. You have to find a good algorithm to make sure that your counting speed is really high. Now, this output topic is processed by another set of function to save them to Redis store, and at the same time generate the metrics that we just saw. Now the UI is mainly made of a geospatial lookup into the business location database. And then once we know what businesses are nearby, we look up their business ratio and display them on the map. So the convenient monitoring and adjustment functionality allow us to test the throughput of the system with different level of parallelization. We see that with a 3-broker setup, now all the calculations are done on the Pulsar broker themselves, not on additional nodes. You can actually reach 13,000 events per second processing rate, which is actually really fast. Now, one problem associated with computing on the topic is the topic themselves, because they're compressed messages, they're already strings, right? Binary strings. So there has to be some schema involved to depack the message into some understandable format. Now, you don't really want to rewrite a different function every time you change the schema of a topic, or rewrite a function for every single different topic. Now, the way we do this is to have a base level of a base function that process the schema information and deconstruct the message back into objects. And the higher level function that's built on top of this can just do your business logic, doing their counting, maxing, or saving some data to database. Now, this is the overall system setup. You have 3 broker nodes, 3 zookeeper nodes, and 3 bookkeeper nodes for the storage. Another node is used as a producer to simulate stream of user input, and yet another node is used as app server to handle the web traffic. To sum up, we have actually built something really simple with pretty much just one tool, Apache Pulsar, that achieve the functionality of a messaging framework, stream processing, and at the same time intermediate databases, all in one piece. At the same time, because we have leveraged the Pulsar functions flexibility to implement very good algorithms, we can reach really high efficiency even with this simple setup. Now, finally, about me, I am a theoretical chemist for 11 years. I have most recently working on using GPUs to accelerate quantum mechanical calculations. It used to be you have to wait for those calculations to finish in many days. Now that we can run them thousands of times faster, the problem becomes when you have that much information coming in, how to process them. And that led me to data engineering. And also you see here, these are my 2 kids. I found that raising kids is very much like building a program. In that beginning, you try to teach them to do stuff. They just don't do anything. They yell at you with system errors, right? But after a few years, all of a sudden they start to work, right? They do amazing things, and that is really a rewarding experience, just like building a product and making them work. Now, thank you for your attention. If you have any questions, please contact me. Thank you.